About E1 and E2 or elimination reactions. So when we looked at SN1 and SN2, you took an alkyl halide and you turn it into something else. You have a nucleophile that comes in and either bonds to the carbocation or bonds to the carbon and kicks off the leaving group, depending on if you're in SN1 or SN2 conditions. Well, the same nucleophile can also do elimination reactions based on the situation, the environment, and things like that. One of the keys is, because what you're going to see is the same nucleophiles, the same alkyl halides, whether they're primary, secondary, or tertiary, is temperature. If it's a high temperature, it's usually going to push it towards the elimination side. And if it's a low temperature, like room temperature, it's going to, or even lower, not even lower, but room temperature or 60 degrees Celsius, something like that, it's probably going to stay more to the substitution side. In an elimination reaction, your alkyl halide turns into an alkene. Okay, alkyl halide to alkene. So the first one we're going to look at is an E2 reaction, okay, which stands for elimination by molecular reaction. Okay, so E2, the rate of the reaction is directly related to the concentration of your reactant and the concentration of the OH-, which means it happens in one step. It's a bimolecular, it's going to happen in one step. Your leaving group's going to leave and we're going to form the double bond. The nucleophile here, instead of attacking to the carbocation, is going to look to remove a hydrogen or something from a leaving group and turn into water, from the carbon, I should say, not the leaving group. The leaving group will leave, the OH will take a hydrogen, and that's how we'll form the double bond. So essentially what's going to happen here, so I have a carbon, okay, so here's my carbon, bonded to a bromine, all right, so it says it's 1-bromo, 1,1-dimethyl-ethane. So if I take my pointer here, or my little pen, the best I could do, let's say this is the hydrogen, and these are the R groups, okay, just for what's going on. So if this is happening in one step, the bromine is leaving, and the reason the bromine is leaving is because the OH is attacking the hydrogen and stealing the hydrogen, and these electrons are coming down to make the double bond. Okay, so we're getting a double bond, and I did it the wrong way. Let me undo that. Let's get the eraser here and just boop, boop. And actually, it would be making the double bond with the methyl group. Just so I'm doing it correctly, it would be coming right here to make the double bond there. Okay, so one step. The OH attacks the proton. The electrons from the proton kick down to make the double bond, which kicks off the leaving group. That's why Br- is over here like so. H2O is formed, and you have your alkene formed. Okay, so like I was telling you, the one student I had at one point in time basically said, well, how is that bromine balanced and things like that? And what is happening here is, don't forget this OH had some sort of cation over here with it to get it to the party, which would balance out that bromine negative. Okay, so that's what's happening in elimination. Yeah, but hey, how do I know? Like, this could also be a substitution reaction. You're absolutely correct. And the thing is, you're going to get substitution and elimination products. And like I said, if you want more or less of the other, temperature could play a very good role in it. Okay. And this is showing exactly what I just showed you. Okay. In an elimination E1 reaction, okay, so the only thing that plays a role is the concentration of the reactant in an E1. Okay, how do I know I'm going to do an E1? My nucleophile is not so great. Okay, good nucleophile, probably going to point to E2, and we'll talk about all that. But it's going to happen in two steps. Okay, a two-step reaction where a carbocation is going to form. Okay, so first step, the bromine leaves. Now, why is the bromine going to leave? I've got to be in a protonated solvent. I've got to be in something that's going to rip the bromine off. So step 1, the bromine leaves. Okay, creating the carbocation. Step 2, the water comes in and removes the hydrogen. Step 3, the double bond is formed. How are these balanced out? Well, you got an acid and a conjugate base. Okay, they're partnered up. You might have some HBr in there. Again, since I'm in a water solvent or something like that, it's going to be dissociated into the hydronium ion. Okay. So what happens? How do we know what's going to be our best product and everything like that? We have an alkene. Which way am I going to go? All right, am I going to make the double bond here? Am I going to make the double bond here? Which is going to be the best? Okay. Well, both are possibilities. So I could have 1 butene. I could also have 2 butene. And I could have 2 butene in the trans form, or I could have 2 butene in the, cis form or in the trans form. The rule is this if I have an option. The most stable alkene is the major product, and how I tell which one's the most stable. The one where the double bond is with the more alkyl substituted carbons. So here's my choices, A and B. Okay, this has 3 hydrogens coming off of it. Okay, H, H, and H coming off of that carbon. This carbon has a CH3 coming off of it. So my double bond, this is going to be the better one because it's the more alkyl substitute in the major product. It's not saying that we won't make any of the one, but it would prefer being in this, and it would prefer being in the trans. Okay. So look at that. If you have a choice, your major product is going to be the alkyl substituted. Double bond. Okay. So we have competition between SN1 and E1, like I said, and SN2 and E2. I'm in the good conditions for SN2, but it also could go E2. So SN2 and E2 are favored by high concentration of a good nucleophile and a strong base. So you want to mark these down. If I have a really good nucleophile, and go back through your notes and see that a good nucleophile is going to have a full-blown negative charge on it. Okay? So a strong base, sodium hydroxide. All right. SN1 and E1 are going to be favored by poor nucleophiles, weak bases. Okay, SN1's 2-step. I really don't need a good nucleophile. I'm not doing everything in one step. I could wait till the carbocation forms. Okay. So if we look at something in SN2, E2 conditions. All right, so let's take a look. This is a primary alkyl halide. This is a secondary alkyl halide. And this is a tertiary alkyl halide. Okay. So primary, secondary, tertiary. If I'm primary, okay, and I'm in SN2, E2 conditions, the majority is going to be SN2. We're going to do substitution. All right, is going to be the major, while elimination is going to be the minor. Move to a secondary alkyl halide. Okay, E2 is going to be, so there's going to be factors of how you know what's going to form. E2 is going to be the major, while the SN2 is going to be the minor. If I'm tertiary, I got one choice in SN2, E2 conditions, because we're talking one step. Steric hindrance is not going to allow. So we're going to all be E2. Okay, so primaries in E2 conditions are going to go major SN2. Secondaries are going to be major E2. Tertiaries under one-step conditions, all E2. When we get to SN1, E1 conditions, it's usually a 50-50 substitution elimination products forming. There is no major minor. We'll get both the substitution and the elimination reactions equally. This slide, okay, which is slide, give me a second here, 55, in the last slide of the presentation, basically is telling you all of the things you should be looking for, whether to determine SN1 and SN2. The one thing this slide is missing is this, okay, is SN, low temp, E is going to be favored in high temp. So even with all the other factors, if I increase the temperature, okay, I could override the SN and make it go E. Or at least level it off, not making it the major, but it would prefer to do that at higher temperatures. Okay. All right. So that does the elimination reaction.